Welcome everyone to our presentation on segmenting credit card users for targeted advertising. My name is Aaron and I'll be going through our introduction. My fellow colleagues in Group 1 for this presentation are Joel, Rabia, Soyuz, and Sayeli. So throughout this project, we'll be going through our introduction and background, objective and business question, data mining, data exploration, data preparation, clustering with k-means, hierarchical clustering, evaluation, and deployment and recommendations. Credit card issuers face a demanding task to try and determine how to spend their advertising dollars. Given that there are hundreds of credit card issuers in Canada and millions of active credit cards, users are likely to be bombarded with advertising, especially if they have credit cards from more than one issuer. This presentation will evaluate potential methods of grouping credit card users based on usage patterns, so advertisements have a firm idea of who their target audience is for any particular campaign. This is a richly competitive environment as there are hundreds of institutions in Canada that issue credit card products with 75.8 million credit cards in active use and 5.5 billion annual transactions. To accurately group customers by usage patterns, we need to determine which factors are the most significant characteristics of a group and which groups comprise the largest segment of the issuer's clientele. A manager at a credit card issuer is having difficulties meeting recruitment targets for new clients and is stumbling when attempting to retain current customers with new targeted services. If they are able to target their advertising, less revenue would be needed to spend, and targeted campaigns can be utilized to get more results. And this brings us to our business question. How can we group customers into groups for targeted advertising campaigns? This project will be done in a series of phases along the industry standard CRISPian framework. Firstly, we'll be conducting an exploratory data analysis to understand the data as presented to us, which Joel will provide more information on.
Our data comprises the bank's database for 8,950 customers, all of whom are still current. The most valuable data, though, is the content found in the features categories that really capture usage patterns. We'll look at things like credit limits, balances, cash advances, installment history, payment history, and tenure. Exploring the data, we learn that the average customer carries a $1,000 balance the majority of the time, makes some cash advances of up to $1,000, has a credit limit of $3,800, and uses a card every month for both one-off and installment purchases. Interestingly enough, some customers take cash advances of up to $50,000, carry balances in excess of $17,000, and some went an entire year without a transaction. While the majority of customers have a credit limit of less than $5,000, some have up to $30,000. We're also able to find no correlation between those who make minimum payments and those who make many installment payments, leading us to believe that payment history must not be the only way we can group our customers. Still, we need to know who are our customers and what characteristics do they have. Looking at each individual category and plotting them out, we found that most of the features of our data are only loosely correlated with others. The purchases are unsurprisingly strongly correlated with the one-off purchases and strongly non-correlated with the tenure, meaning someone with a lot of purchases is also someone likely to have a lot of one-off purchases but may or may not have any loyalty to the card issuer. Our initial hypothesis is that features like that, though highly correlated with each other, don't fully represent the clients. We also surmise that there could be better factors included in the data to better segment the customers. Our data is pretty clean, but we could make it better. Given the significant outliers in the data, our information is skewed highly to the right in features where the data is represented by a whole number, such as the top example, cash advance. In the bottom example of purchase frequency, the data is represented by a ratio, so we are much more apt to find a distribution where the data is concentrated along the edges. In the future, such multimodal distributions could potentially be used to convert the features to a binary category. Almost every missing value is concentrated in the minimum payments category, and it comprises less than 4% of the data in that category. Given the significance of the outliers and to avoid biasing the distribution even further, the missing values were imputed from the median value for the category. Here we have a graph of all the missing values. As you can see, once the missing values for all features were imputed, we dropped the customer ID on the column on the far left from the dataset. The customer ID is an arbitrary number assigned to the customer and has no relationship to the remaining attributes. To normalize the data and prepare it for analysis, we had two final steps. Firstly, 14 of the features needed to be classified into a range value, or bin, so as to minimize the effect of the outliers. So now someone with a credit limit of $30,000 is classified the same as someone with a credit limit of $10,000. Another way to look at it is that these two people are merely classified as having a high credit limit. Secondly, we had to scale the data. The process of scaling ensures that all features receive the same importance from the model. We chose a standard scaler. We initially thought a robust scaler would be ideal, but we found that it invalidated some of the data and poorly represented the actual customers. I'll pass it off to Rabia here to talk about the first algorithm we used for clustering our customers.
Thanks a lot, Joel. The objective of k-means clustering is quite easy to understand. It tries to group similar data points together to discover underlying patterns. To achieve this, we need to find the optimum number of k, also known as centroid. It locates every data point to the nearest cluster by reducing the in-cluster sum of squares. The number of clusters is only limited by the size of data set. For example, it makes no sense to have more clusters than you have in your data points. But the ideal number of clusters is found at the elbow using the elbow method. As shown in the graph, our ideal number of clusters is likely around 6. Given the iterative nature of k-means, it can be inconsistent. The result is often the product of initialization where the centroid are placed. It may get stuck in a local optimum and not a global optimum. So once we have the optimal number of k, we go to the next step of cluster interpretation and visualization. In these graphs, we can plot each feature of each cluster and try to extract value and meaning to interpret what each cluster means. So we look at each feature to try to interpret. By doing this, we go to the next step of visualizing clusters and defining what each cluster means. In this slide, and from the previous slide, we find the general characteristics of each clusters, and they are as follows. Cluster 0, group of customers with high balances, many purchases, high credit limit. Cluster 1, group of customers with low balances, low purchases, and low credit limit. This cluster is bank's least favorite and is recommended to the bank to target this group of customers. Cluster 2, group of customers with high credit limit, low value transactions, and many installment purchases. Cluster 3, group of customers with high credit limit with a lot of cash advances. And cluster 4 is a group of customers with high credit limit, high purchases, high installment purchases, and a lot of cash advances. This cluster is bank's favorite group, also known as high spenders. And last but not least, cluster 5, group of customers with average credit limit, most cash advances, and not much spenders. Now I'll pass it off to Sayuz, who will talk about hierarchical clustering.
Thank you, Rabia. For this data set, we also performed a hierarchical clustering analysis. Hierarchical clustering creates a hierarchy of clusters. For the analysis, we first scaled and normalized the data, then reduced the dimensionality to 2 using principal component analysis. The PCA scree plot indicated that the two principal components account for 55% of the variations of the original data. For the hierarchical clustering, we performed an agglomerative hierarchical clustering. It is a bottom-up approach where players of clusters are merged as one moves up the hierarchy. To visualize the data and the possible number of clusters, we created a dendrogram. We then cut the dendrogram with a horizontal line to create significant clusters. The dendrogram of the data shows that there are at least 5 to 6 possible significant clusters in the data. Next, we ran various agglomerative hierarchical clustering models using k equals 2 to 9 and compared the quality of the models using silhouette scores. In clustering analysis, silhouette scores can be used to measure and evaluate the separation or distance between the created clusters. The closer the value to +1, the more accurate the number of clusters. Based on the silhouette scores, k equals 6 seems to create the optimum number of clusters. To sum up, we used an elbow plot and silhouette score plot to gauge the optimum number of clusters in both clustering models. While k-means requires k as an input before running the k-means clustering model, hierarchical clustering doesn't require a k input before creating a dendrogram. In both cases, k equals 6 provided an optimum number of clusters.
Deployment and recommendation. We recommend utilizing the k-means to segment the customers into cluster for advertising purchases with the following consideration. The model is only valid at the time it is run. Rerunning the algorithm repeatedly could give different results. Since k-means is iterative, unless the initialization parameters are constant, the initial location of centroid is variable. Develop a framework of advertising techniques for characteristics of clusters. Customers can meet the criteria to belong to different clusters. Care must be taken not to pigeonhole these customers too tightly when attempt to develop marketing strategies. Insight and deployment of model. Use data for more than the previous 12 months to better identify high danger customers. Categorize the data into bins or ranges when retaining the data, for example, credit limit. Explore the possibility of capturing geographical information in an ethical way to add another dimension of the data. Explore the possibility of the cross-referencing the current customer database with population densities to determine regional saturation of the credit card products.
So to conclude, based on our clustering analyses, groups of credit card customers were identified for targeted advertising campaigns, such as customers who make expensive purchases, customers who have high cash advances, customers who purchase mostly in installments, etc. Furthermore, segmenting customers can help our client not just create advertising campaigns, but also to create strategies to retain current customers and recruit new customers.